Hi, my name is Pavlidis, and I'm an assistant professor in the Department of Electrical and Computer Engineering at North Carolina State University. Today, we find ourselves in the Laboratory for Electronics in Advanced Devices and Systems, known as NC State LEADS. In this lab, we specifically do electrical characterization and testing of semiconductor devices used in electronic components. Today I'm going to demonstrate to you some of the testing that we do on wide bandgap semiconductors for power device applications. I'll start off by explaining to you a little bit about why this testing is important and at which point in the development of semiconductor devices we do it. Then I'll talk to you about the probe station that is to my right, as well as the semiconductor parameter analyzer that is to my left. And at the end, we'll take a look around the corner to see a pulsed IV system that we can also use for high speed and high power characterization of power devices. When you open up a power electronics component, like a cell phone charger for example, you're probably going to find a printed circuit board, and attached to that printed circuit board are going to be a variety of different components like resistors and capacitors, as well as active semiconductor devices like diodes and transistors. These active semiconductor devices are packaged when they're put into a printed circuit board, and they look like this. You can see that none of the sensitive components and materials are open in the air. They've been wrapped up in a protective film, and all we have access to are three different leads. This is an example of a silicon carbide transistor. So we have the gate, drain, and source connections available to us through these leads. And of course, before a company ships such a component to a customer, they test the component in this packaged form. But before it can be put into this packaged form, we make devices on wafer. This is an example of a 6-inch silicon wafer, on which silicon electronics can be fabricated, as well as GaN-on-silicon devices. Wafers of this type can be found in other materials, like silicon carbide as well, and in general, all semiconductor devices are fabricated in a flat form factor like this on wafer. After we complete fabrication, and during the fabrication itself, we have to perform electrical characterization. This allows us to assess the quality of the materials and the quality of the fabrication steps as the process is executed. So usually, a fabricated wafer will consist of not only finished devices like transistors and diodes, but will also consist of test structures that allow us to isolate problems that we might be observing in larger devices. So the question that I'll be trying to answer today through this demonstration is how can we test these types of devices when they're on wafer? And I'd like to point out that testing on wafer doesn't only refer to testing on a full circular substrate like this one, but it can also be testing on a smaller substrate. Here, for example, are two pieces that have been cut out of a wafer. These are 1-inch by 1-inch substrates on which fabrication has been performed. And you can see here some of the metal lines that reflect back out at you where the contacts of these devices are located. Smaller still, we can make individual dies as they are known. And dies can consist of multiple devices, or in the case of large, high voltage, high current power devices, can be a singular device. This, for example, is an example of a silicon carbide vertical transistor that is commercially available in today's market. So you can say that the features here are quite small, and we need a way to precisely access these features and individually apply voltages and currents, as well as measure voltages and currents on these devices. And that's what the probe station and the semiconductor parameter analyzer that I have here are for. All right, I've gone ahead and opened up the enclosure in which the probe station can be found. The probe station is this entire system that's located in the middle here. There's a couple important things to pay attention to. First of all, there's a microscope. The microscope allows us to carefully zoom in and look at the small features that are on the surface of our wafer. This is especially important because oftentimes the features are on the micron or even nanometer scale. So we look through the eyepiece and place the substrate underneath the microscope on a metallic plate known as the chuck. I've actually already gone ahead and placed a semiconductor piece on the chuck. Now, to actually perform testing, we need to somehow interface with that device electrically. And what you'll see here are these three components. These three components on the outside are known as micropositioners. Micro because they allow us to have micrometer precision over the movement, and positioners because we are trying to position a probe. A probe is a needle with a very fine tip. It's a metallic needle which will touch down or probe the device. And it's through that probe that we apply voltages and measure currents, for example. We will be testing a 3-terminal transistor today, so I've set up the probe station with 3 different positioners and 3 different probes. From each one of these probes, you'll notice that there are cables running out of the probe station and into the neighboring semiconductor parameter analyzer that we'll take a look at next. Another interesting feature to pay attention to is the fact that we have an interlock. This interlock has been installed on the enclosure. The interlock serves to increase the safety of operating this system. And this is particularly important in high voltage applications that we use to test high voltage devices. High voltages can be dangerous to the operator, so we don't want the device to be live or active unless we know that the operator is at a safe distance. So what this interlock does is it senses whether or not the doors of the enclosure are closed. If the doors are closed, it actually sends a signal to the semiconductor parameter analyzer and tells it that it's safe to proceed with the measurement. However, if the doors are open, then even if an operator were to initiate a measurement, the interlock would supersede that command and stop the measurement from proceeding. I also want to mention a couple things about the enclosure itself. I've already talked about how the enclosure serves a purpose of safety, to keep the operator isolated from the devices and the measurements. There's also a second purpose. This enclosure is also known as a Faraday cage. It's basically a metallic cage or a metal box. That allows us to improve the precision or accuracy of our measurements by reducing noise that might be interfering with the device. Noise can come in the form of electromagnetic noise that's present in the air from your cell phone, for example, or a base station that's nearby. But it can also come from ambient light that might interact with your device. We want to try to isolate these variables so we can really look at the intrinsic performance of the semiconductor devices that we're testing. In today's demonstration, we will be measuring the IV characteristics of AlGaN-GaN HEMTs on silicon. The devices that we have available to us here consist of 3 different transistor types. The first type is the recessed gate misHEMT. The second type is the regular HEMT, and the third type is the non-recessed gate misHEMT. The recessed gate misHEMT is one type of gate architecture that can be used to achieve normally off behavior or E-mode behavior necessary for power applications. This device down here, the traditional HEMT, that does not use a recess or an insulator at the gate, relies on a Schottky contact at the gate and is a normally on device. This is the mask set that is used to produce these devices on wafer. The first row up here are a series of devices for the recessed gate misHEMTs that we expect to be normally off. The row devices are the traditional depletion mode or normally on HEMTs. Down here, we have some devices with multiple fingers or multiple channels that would allow us to scale up the current handling capability of the device. And down here, we have some devices that consist of a gate insulator but do not have a gate recess. Outside of the transistor structures, our mask set includes a number of other test structures that can also be used to analyze the quality of the materials and the quality of the fabrication process as it is executed. These include things like an MIS capacitor, a recessed MIS capacitor, a Schottky diode characterization structure, transfer length method or TLEM test structures used to test the contact resistance and quality of the ohmic contacts. These particular ones over here are rectangular in nature, whereas down here at the bottom we have a series of circular TLM structures. We also can make MESA breakdown voltage test structures, MIM capacitors, and then up here in the top right is an alignment mark that we use to align our sample when using the stepper, since the stepper is used in a couple of our fabrication steps but not all the way throughout. And on the left over here are a series of alignment marks to align the various layers when using the regular photolithography mask aligner. In today's demonstration, we're going to start off by testing the IV curves of one of these depletion mode HEMPs, namely FET07, and then we're going to test the equivalent enhancement mode or recess gate HEMPs to confirm that this produces normally off behavior. This is a zoomed in perspective of FET07 that we'll be testing, and you'll see what this looks like under the microscope once the device is being probed. Okay, here's a closer look at what's going on the surface of the probe station. You can make out the 1, 2, and 3 probes that I was referring to earlier, as well as the objectives that we have in the microscope. At the bottom here is the piece of wafer with the fabricated devices on it. And you can see that the probes are located just above that. I've already aligned the probes by looking through the microscope just a moment ago, and what I'll do now is I'll go ahead and lower the probes down using a lever that's on the edge. You'll notice here that the probes are coming down to the surface, and at a certain point they'll finally touch the surface of the device and make contact. It's at this point that I can begin testing. This is what things look like under the microscope. You can see that we're going to test FET07, and the transistor has one contact pad for each one of the terminals of the device. Here we've got a contact pad for the gate, one for the source, and one for the drain. And to each contact pad we've landed a probe, here, here, and here. We're going to use these probes to apply voltage biases and measure currents at each one of the terminals. Before moving forward with the measurement demonstration, I want to point out that the contact pads themselves have a nice smooth finish, but we also see these rougher regions that are represented in each and every one of the devices on the wafer. This is actually intentional and highly desirable, as it is a visual cue that we have successfully performed contact alloying at the source and drain terminals. Contact alloying provides us with a low contact resistance ohmic contact for those source and drain terminals, which is necessary for successful transistor operation. So let's go and walk over to the semiconductor parameter analyzer and take a look at how setup is done for a measurement. So here we are in front of the semiconductor parameter analyzer, and you can see that this is basically a Windows PC with a highly integrated measurement interface. In this particular window that we're looking at, we're in the configuration mode where we get to define what our measurement looks like. And this software has already been told that we'll be testing a field effect transistor type of device. And so it knows that it needs to have 3 different terminals, namely a gate, a drain, and a source. For each of those, we get to define what those terminals are going to be doing. So in the case of the gate, we get to define that we will, for example, do a sweep of the voltage while holding the drain terminal at a constant voltage bias. This particular device that we're going to test first is a depletion mode device, otherwise known as a normally on device. This means that the threshold voltage of the device is negative. So we will test this device from -5 volts to 0 volts at the gate while keeping a constant drain bias of 0.5 volt. Let's go ahead and hit play to see what the result looks like. This is what the measurement looks like going live. It's kind of hard to see what's going on the x-axis, but the x-axis is showing you gate voltage. On the left-hand side over here, it's -5 volts, and on the right-hand side over here, it's 0 volts. And the y-axis over here is showing drain current, and it's on a logarithmic scale. So we can see that in the off state, this device is currently showing an off current that is in the nanoamp range, and in the on state, it turns on by several orders of magnitude and ends in the 10 milliamps range. The transition point at which the current starts to increase significantly occurs at around -2.5 volts. So this confirms that this is a depletion mode or normally on type of device. Of course, we can visualize this data in other ways as well. So for example, we can go over here and change the axis for the y-axis to be a linear axis. And we can see that the threshold voltage, if we take it to be the x-axis intercept, is around -2 volts. What that threshold voltage is that you want to report is something that needs to be defined quite precisely. And you can see here between the semi-log plot and the linear plot here, there are some differences in how that threshold voltage can be defined and interpreted. Nonetheless, there is no doubt that this is a depletion mode device. Now, in this particular measurement, not only did we sweep the gate voltage and measure the drain current, but we also measured the gate current. So we can define the graph here and add in the gate current to the plot, and you can see what the gate current looks like. And this is, again, nanoamp regime type of currents. Due to the differences in the way the axes are scaled, they look like they're quite similar, but everything that you're seeing on the second y-axis to the right is in the nanoamp range. The semiconductor parameter analyzer also has the ability to perform some calculations of parameters on the fly. So we can also look at something like GM, transconductance, and plot that here. And you can see here a plot of the transconductance overlaid on top of the transfer curve showing the transconductance as a function of the gate voltage. All of this information can be exported from the semiconductor parameter analyzer and then analyzed on a computer or some other software that you want to use. Of course, this is only one demonstration of a measurement that can be done. There are so many other types of measurements that can also be done on a semiconductor parameter analyzer, including breakdown voltage measurements where a large voltage is applied across the device, increasing until the device's current starts to increase, indicating the beginnings of breakdown, capacitance voltage or CV measurements, or even pulsed IV if you want to look at different things that might be impacting the device's performance, like trapping. Many of these measurements can be done directly with the semiconductor parameter analyzer without having to adjust or move to other types of equipment. Now I'm going to go and adjust the probe station and take it from probing a depletion mode device to probing an enhancement mode device, since enhancement mode devices are favorable for powered device applications. The probe station has now been adjusted from probing a depletion mode device that we looked at a moment ago to now measuring an enhancement mode device. We'll now use the semiconductor parameter analyzer to confirm that this device is indeed an enhancement mode device with a positive threshold voltage. Just like before, we are now running a sweep of the gate voltage while maintaining a constant drain voltage bias. On the left-hand y-axis, you can see the drain current, and on the right-hand y-axis, you can see the transconductance. The measurement has just been completed. The left-hand corner of the x-axis is at -2 volts, and the right-hand corner is at 3 volts. And you can see that the peak transconductance occurs just above 1 volt, and that would be approximately where the threshold voltage could be extracted from. So this confirms that this device is definitely a device with a positive threshold voltage at around 1 to 1.5 volts, which makes it a normally off device or an enhancement mode device that is favorable for power electronic applications. I have now reconfigured the semiconductor parameter analyzer to measure the breakdown voltage characteristic of this device from 0 to 200 volts. This particular semiconductor parameter analyzer is limited to 200 volts. Because this is an enhancement mode device, I can measure the device with a 0 volt gate bias. Here is a graphical representation of that breakdown voltage measurement. You can see the drain voltage on the x-axis going from 0 to 200 volts, and on the y-axis on the left-hand side, the drain current. The drain current is saturated and remains small at around 300 nanoamps all the way up to 200 volts. Therefore, this device has a breakdown voltage which is larger than 200 volts and requires an additional piece of equipment to be measured. Other semiconductor parameter analyzers provide modules that allow you to measure beyond 200 volts. In this particular case, such a module does not exist, so instead we have to rely on an external power supply to supply that larger voltage in order to test the limits of the breakdown voltage response of this type of device. The 2657 here is one example of such a power supply, and it's capable of providing a few thousand volts of bias while measuring very small currents needed to measure the off state of the device and indicate to you precisely when breakdown voltage will occur. The nice thing about the semiconductor parameter analyzer, since it basically acts like a computer, is that it can coordinate the measurement between itself and any voltages that you're applying through it, for example, a gate voltage at a lower voltage, as well as the larger voltage 2657. In addition to using the right kind of measurement equipment, we also have to go back to think about the measurement setup itself. As you go to higher and higher voltages, you risk the air around the device breaking down, which would actually increase the current before the device breaks down. To combat this, we can use a liquid to protect the device. This particular liquid is called fluorinert, and we would extract a droplet or two, or maybe even an entire volume that would surround the wafer, so the wafer is immersed inside of it, and we would probe through the liquid onto the pads as we did earlier. This liquid, fluorinert, does not break down until very high voltages, and so it would ensure that any breakdown characteristic that we see is really due to the device itself breaking down. This is an example of a pulsed IV system. This type of measurement is different from what we saw earlier, since the semiconductor parameter analyzer traditionally allows us to apply a constant voltage bias and measure a constant current. These are really DC measurements. In a pulsed IV measurement system, we're applying square waves of voltages known as pulses, and we can control the width or duration of those pulses down to less than a microsecond. In order to test in this particular setup, we've actually gone ahead and wire bonded a very similar AlGaN-GaN hemp to the one that we saw earlier onto an aluminum nitride board. That allows us to then connect the pulsar heads shown here for the gate and drain, or the input and the output, to the board onto which the die has been attached and wire bonded. The pulsar heads have to be as close as possible to the device itself in order to provide a clean square wave, especially as that pulse width gets smaller and smaller. So overall, what we're able to do is a variety of different measurements applying dynamic conditions, and that allows us to understand the dynamic response of these devices. Two examples of that you can normally see in papers or in product sheets are, number one, looking at the duty cycle dependence of a device. That means comparing a device in which the device is on for 1% of the time versus a device that might be on for 10% of the time. So that would mean for a fixed period, you're adjusting the pulse width that's applied. And if you see that there's a difference in the device's performance, that means that there's something going on inside that device, for example, surface traps, that might be affecting its stability. Another type of measurement that is very common to do with these types of measurements is called a dynamic RON measurement. Because we're using a pulse, we can actually switch between two different voltage states. And in a dynamic or-on measurement, what we would do is we would apply a very large voltage, which would represent the off state or the blocking state, and then jump to a very low voltage, which would represent the on state. And if we see that there's a dependence on the on state current and the off state blocking voltage, then we know that there's again a dynamic response going on there that might be due to traps at the surface or traps at the gate or some other intrinsic effect within the device that we need to further optimize. Another neat thing about pulsed IV systems is that they allow us to apply very large currents, and that's because we control the heating through the control of the pulse width. So now let's take a look at a quick measurement that we've done here and show you how the pulse width can impact the device's performance. This is an example of a pulsed IV measurement performed to capture the output characteristic of an AlGaN-GaN HEMT. On the x-axis, you'll notice that we're plotting the drain voltage, and on the y-axis, we're plotting the drain current. You'll also notice that in the label for the drain voltage, we have an underscore NQ. This indicates that we are plotting the non-quiescent voltage that is applied during each progression of the drain voltage sweep. In between this non-quiescent voltage, we return to a quiescent voltage, which is kept constant throughout the measurement. Each drain voltage sweep is conducted with a constant gate voltage bias, and you can see a family of curves in this plot. We're using gate voltages of -3, -2.8, -2.6, and -2.4 volts. From this, you should be able to tell that this is indeed a normally on or depletion mode device, since negative gate voltages are able to induce large drain currents. You'll also notice that for a given gate voltage, we have two different curves. That's because we've conducted this measurement twice, once using a duty cycle of 0.1% and another time using a duty cycle of 1%. And we can see there's actually a difference between the drain current depending on the duty cycle. This is known as current collapse and would be indicative of traps inside of a device that need to be addressed during the fabrication process. In addition to looking at whether or not there is current collapse in this device, which is observed in the saturation region up here, we can also go down to the low drain voltage area and look at the slope of the current. This would indicate what the on resistance of the device is, which is an important parameter of any power device. Moreover, you'll notice that there is this red dashed line that comes down here and forms a boundary for this measurement. This is a power compliance that we can set to further protect the device. At lower voltages, gate voltages, when the drain current is small, we see that the power is quite small, and therefore we can conduct the sweep over the entire 20-volt range that we've defined. However, if we're concerned about the device overheating due to an excessive amount of dissipated power, we can define a power compliance or a maximum power limit for the measurement, which is defined by this curve here. And so you'll notice that as the current gets larger and the power compliance is met, the measurement will stop at a smaller drain voltage. This concludes this demonstration. Today, we started off by looking at how we can test power devices on wafer by using a combination of a probe station and a semiconductor parameter analyzer. This allowed us to look at the low voltage behavior of these devices first and confirm, for example, where the threshold voltage is. In the case of an AlGaN-GaN HEMT, we confirmed that by using a recessed gate structure, we can achieve normally off behavior or an E-mode type of device. Then we explained that further modifications to the test setup can be made in order to test at even higher voltages. Number one, we can use a high voltage power supply. And number two, we can introduce something like floor inert to ensure that we don't break down the air before we break down the device itself for the measurement. After that, we came over here and we took a look at this pulsed IV system, which allows us to test a package device. This was an AlGaN-GaN HEMT that was wire bonded on an aluminum nitride substrate. And by using these dynamic square waveforms, we can look at the dynamic behavior of a device. Once all of these characterization steps have been done and the device clears these tests, we can then proceed with packaging them inside of a commercial package. This takes us back to the beginning of this video, where we would be testing a device like this, putting it inside of a printed circuit board, in which case the measurement would be done on this kind of scale. We'd introduce different types of power supplies, different types of loads, and use something like an oscilloscope to measure the waveforms, understand things like reverse recovery, for example. I'm not going to talk about all of these today, but I hope that you now have an appreciation for how characterization can be done at the wafer level, and how we can then pass the devices on to the circuit level for further characterization and validation before integrating them into a power electronics module.